improve your memory. We are constantly being bombarded with physical stimuli, patterns of touch on our skin, light to our eyes, light to our skin for that matter, smells, tastes, and sound waves. Each one of and all of those sensory stimuli are converted into electricity and chemical signals by your so-called nervous system, your brain, your spinal cord, and all their connections with the organs of the body, and all the connections of your organs of the body back to your brain and spinal cord. For instance, if you can hear me speaking right now, you are perceiving my voice, but you are also, most likely, neglecting the feeling of the contact of your skin with whichever surface you happen to be sitting or standing on. It is only by perceiving a subset, a small fraction of the sensory events in our environment, that we can make sense of the world around us. Otherwise, we would just be overwhelmed with all the things that are happening in any one given moment. Now, memory is simply a bias in which perceptions will be replayed again in the future. Now, this might seem immensely simple, but it raises this really interesting question, which we talked about before, which is why do we remember certain things and not others? Because according to what I've just said, as you go through life, you're experiencing things all the time. You're constantly being bombarded with sensory stimuli. Some of those sensory stimuli you perceive, and only some of those perceptions get stamped down as memories. Today, I'm going to teach you how certain things get stamped down as memories. And I'm going to teach you how to leverage that process in order to remember the information that you want far better. Each individual thing that we remember or that we want to remember is linked to something by either a close, a medium, or a very distant association. This turns out to be immensely important. I know many of you will read or will encounter programs that are designed to help you enhance your memory. You know, you have these phenoms that can remember 50 names in a room full of people, or they can remember a bunch of names of novel objects, or maybe even in different languages. And oftentimes that's done by association. So people will come up with little mental tricks to, either link the sound of a word or the meaning of a word in some way that's meaningful for them and will enhance their memory. That can be done and is impressive when we see it. And for those of you who can do that, congratulations. Most of us can't do that, or at least it requires a lot of effort and training. However, there are things that we can do that leverage the natural biology of our nervous system to enhance learning and memory of particular perceptions and particular information. So let's talk about tools for enhancing memory. Now, there's one tool that is absolutely clear works, and that's repetition. The more often that you perform something or that you recite something, the more likely you are to remember it in the future. And while that might seem obvious, it's worth thinking about what's happening when you repeat something. But when I say what's happening, I mean at the neural level. What's happening is that you're encouraging the firing of particular chains of neurons that reside in a particular circuit, right? So a particular sequence of neurons playing neuron A, B, C, D, played in that particular sequence over and over and over again. And with more repetitions, you get more strengthening of those nerve connections. The problem for most people is that they either don't have the patience, they don't have the time, and sometimes they literally don't have the time because they've got a deadline on something that they're trying to remember and learn, or they simply would like to be able to remember things better in general, and remember them more quickly. This process of accelerating repetition-based learning so that your learning curve doesn't go from having to perform something 1,000 times and then gradually over time it's 1,750 times a day, 500 times a day, 300 times a day, and down to no repetitions, right? You can just perform that thing the first time and every time. Well, there is a way to shift that curve so that you can essentially establish stronger connections between the neurons that are involved in generating that memory or behavior more quickly. How do you do that? Well, in order to answer that, we have to look at the beautiful work of James McGaugh and Larry Cahill. James McGaugh and Larry Cahill did a number of experiments over several decades, really, that really established what's required to get better at remembering things and to do so very quickly. They evaluated the capacity for stress and for particular neurochemicals associated with stress to improve our ability to learn information, not just information that is emotional, but information of all kinds. So I'm going to describe some experiments done in animal models just very briefly, and then experiments done on human subjects. If you take a rat or a mouse and put it in an arena where at one location the animal receives an electrical shock, and then you come back the next day, you remove the shock-evoking device, and you let the animal move around that arena, that animal will quite understandably avoid the location where it was shocked, so-called conditioned place aversion. That effect of avoiding that particular location occurs in one trial. That's a good example of one trial learning. So somehow the animal knows that it was shocked at that location. It remembers that. It is a hippocampal dependent learning. They remember it after the first time and every time, unless you are to block the release of certain chemicals in the brain and body. And the chemicals I'm referring to are epinephrine, adrenaline, and to some extent, cortisol. Now, we know that the effect of getting one trial learning somehow involves epinephrine, at least in this particular experimental scenario, because if researchers do the exact same experiment, and they have done the exact same experiment, but they introduce a pharmacological blocker of epinephrine so that epinephrine is released in response to the shock, but it cannot actually bind to its receptors and have all of its biological effects, well, then the animal is perfectly happy to tread back into the area where it received the shock. It's almost as if it didn't know, or we have to assume that it didn't remember that it received the shock at that location. So it all seems pretty obvious when you hear it. Something bad happens in a location, you don't go back to that location. But it turns out that the opposite is also true, meaning for something called conditioned place preference, you can take an animal, put it into an arena, feed it, or reward it somehow at one location, take the animal out, come back the next day. No food is introduced, but it'll go back to the location where it received the food. Or you can do any variant of this. You can make the arena a little bit chilly and provide warmth at that location. Or you can take a male animal, and it turns out male rats and mice will mate at any point, or a female animal that's at the particular so-called receptive phase of her mating cycle, and give them an opportunity to mate at a given location. They'll go back to that location and wait and wait. This is perhaps why people go back to the same bar, or the bar seat at the bar, or the same restaurant and wait because of the one time they, things worked out for them, whatever the context was. Conditioned place preference, as with conditioned place avoidance, depends on the release of adrenaline, right? It's not just about stress. It's about a heightened emotional state in the brain and body. Okay, this is really important. It's not just about stress. You can get one trial learning for positive events, conditioned place preference, and you can get one trial learning for negative events. This turns out all to be true for humans as well. We know that because McGaw and Cahill did experiments where they gave people a boring paragraph to read and only a boring paragraph to read. But one group of subjects was asked to read the paragraph and then to place their arm into very, very cold water. In fact, it was ice water. We know that placing one's arm into ice water, especially if it's up to the shoulder or near to it, evokes the release of adrenaline in the body. It's not an enormous release, but it's a significant increase. And yes, they measured adrenaline release. In some cases, they also measured for things like cortisol, etc. And what they found is that if one evokes the release of adrenaline through this arm into ice water approach, the information that they read previously, just a few minutes before, was remembered. It was retained as well as emotionally intense information. But keep in mind that information that they read was not interesting at all, or at least it wasn't emotionally laden. This had to be the effect of adrenaline released into the brain and body, because if they blocked the release or the function of adrenaline in the brain and or body, they could block this effect. This is absolutely important in terms of thinking about tools to improve your memory. It is the presence of high adrenaline, high amounts of norepinephrine and epinephrine that allows a memory to be stamped down quickly, and far and away different than the idea that we remember things because they're important to us or because they evoke emotion. That's true, but the real reason, the neurochemical reason, the mechanism behind all that is neurochemicals have the ability to strengthen neural connections by making them active just once. There's something truly magic about that neurochemical cocktail that removes the need for repetition. Okay, so let's apply this knowledge. Let's establish a scientifically grounded set of tools, meaning tools that take into account the identity of the neurochemicals that are important for enhancing learning and the timing of the release of those chemicals in order to enhance learning. Caffeine, in the form of coffee or yerba mate or any other form of caffeine, does create a sense of alertness in our brain and body. So my typical way of approaching learning and memory would be to drink some caffeine and then focus really hard on whatever it is that I'm trying to learn, try and eliminate distractions, and then hope, or try to remember that information as best as I could. And frankly, I felt like it was working pretty well for me. And typically, if I leveraged other forms of pharmacology in order to enhance learning and memory, things like alpha GPC or phosphatidylserine, I would do that by taking those things before I sat down to learn a particular set of information or before I went off to learn a particular physical skill. For those of you out there listening to this, you're probably thinking, well, okay, the results of McGaugh and Cahill pointed to the fact that having adrenaline released after learning something enhanced learning of that thing. But a lot of these things like caffeine or alpha GPC can increase epinephrine and adrenaline or dopamine or other molecules in the brain and body that can enhance memory for a long period of time. So it makes sense to take it first or even during learning and then allow that increase to occur. And the increase will occur over a long period of time and will enhance learning and memory. While that is partially true, it is not entirely true. And it turns out it's not optimal. And it turns out that the best time window to evoke the release of these chemicals, if the goal is to enhance learning and memory of the material, is either immediately after or just a few minutes, 5, 10, maybe 15 minutes after you're repeating that information. You're trying to learn that information. Again, this could be cognitive information or this could be a physical skill. Now, this really spits in the face of the way that most of us approach learning and memory. Most of us, if we use stimulants like caffeine or alpha GPC, we're taking those before or during an attempt to learn, not afterwards. If you're using those compounds in order to enhance learning and memory, well, then I encourage you to try and take them either late in the learning episode or immediately after the learning episode. Now, given everything I've told you up until now, why would I say late in the learning episode or immediately after? Well, when you ingest something by drinking it or you take it in capsule form, there's a period of time before that gets absorbed into the body, and different substances such as caffeine, alpha GPC, etc., are absorbed from the gut and into the bloodstream and reach the brain and trigger these effects in the brain and body at different rates. So it's not instantaneous. Some have effects within minutes, others within, tens of minutes, and so on. It's really going to depend on the pharmacology of those things, and it's also going to depend on whether or not you have food in your gut, what else you happen to have circulating in your bloodstream, etc. But at a very basic level, we can confidently say that there are not one, not dozens, but as I mentioned before, hundreds of studies in animals and in humans that point to the fact that triggering the increase of adrenaline late in learning or immediately after learning is going to be most beneficial if your goal is to retain that information for some period of time and to reduce the number of repetitions required in order to learn that information. Now, I want to acknowledge that on previous episodes of this podcast, I've talked a lot about things like non-sleep deep rest and naps and sleep as vital to the learning process. And I want to emphasize that none of that information has changed, right? I don't look at any of that information differently as the consequence of what I'm talking about today. It is still true that the strengthening of connections in the brain, the literal neuroplasticity, the changing of the circuits occurs during deep sleep and non-sleep deep rest. And it is also true, and I've mentioned these results earlier, that 2 papers were published in Cell Reports, Cell Press Journal, excellent journal, over the last few years, showing that brief naps of about 20 to up to 90 minutes in some period of time after an attempt to learn can enhance the rate of learning and memory. That still can be performed, but it can be performed some hours later, even an hour later. It can be performed 2 hours later or 4 hours later. Remember, it's in these naps and in deep sleep that the actual reconfiguration of the neural circuits occurs, the strengthening of those neural circuits occurs. It is not the case that you need to finish a bout of learning and drop immediately into a nap or sleep. Some people might do that, but if you're really trying to optimize and enhance and improve your memory, the data from McGaugh and Cahill and many other laboratories that stemmed out from their initial work really point to the fact that the ideal protocol would be focus on the thing you're trying to learn very intensely, still try and get excellent sleep. Again, fundamentally important for mental health, physical health, and performance. And we can now extend from performance to saying including learning and memory. Nap if it doesn't interrupt your nighttime sleep. Naps of anywhere from 10 to 90 minutes or non-sleep deep rest protocols will enhance learning and memory, but we can now add to that spiking adrenaline, provided it can be done in a safe way, is going to reduce the number of repetitions required to learn, and that should be done at the very tail end or immediately after a learning bout, which is compatible with all the other protocols that I mentioned. And the reason I'm revisiting the stuff about sleep and non-sleep deep rest is I think that some people got the impression that they need to do that immediately after learning, and today I'm saying to the contrary. Immediately after learning, you need to go into a heightened state of emotionality and alertness. Now, it's vitally important to point out that you do not need pharmacology. You don't need caffeine. You don't need alpha GPC. You don't need any pharmacologic substance to spike adrenaline unless that's something that you already are doing or that you can do safely or that you know that you can do safely. So if you're somebody who's not used to drinking caffeine and you suddenly drink 4 espresso after trying to learn something, you are going to have a severe increase in alertness and probably even anxiety. If you're panic attack prone, please don't start taking stimulants in order to learn things better. You could take a cold shower. You could do an ice bath or get into a cold circulating bath in order to evoke epinephrine and dopamine release. You could go out for a hard run. You could do any number of things that would increase adrenaline in your body. Which things you choose is up to you. But the overall takeaway is that anything that increases adrenaline will increase learning and memory and will reduce the number of repetitions required to learn something. And as a cautionary note, don't think that you can push this entire system to the extreme over and over again, or chronically, as we say, and get away with it. In other words, you're not going to be able to take a alpha GPC and a double espresso, do your focused bout of work, cognitive or physical work, and then spike adrenaline again afterwards and remember that stuff even better, right? I'm not encouraging you. In fact, I'm discouraging you from chronically increasing adrenaline both during and after a given bout of work if the goal is to learn. Why do I say that? Well, work from McGaugh and Cahill and others has shown that it's not the absolute amount of adrenaline that you release in your brain and body that matters for enhancing memory. It's the amount of adrenaline that you release relative to the amount of adrenaline that was in your system just prior, in particular in the hour or two prior. So again, it's the delta, as we say, it's the difference. So if you're going to chronically increase adrenaline, you're not going to learn as well. The real key is to have adrenaline modestly low, perhaps even just as much as you need in order to be able to focus on something, pay attention to it, and then spike it afterwards. This is immensely important because while much of what we're talking about is actually a form of inducing a neurochemical acute stress, meaning a brief and rapid onset of stress, well, chronic stress, the chronic elevation of epinephrine and cortisol is actually detrimental to learning. And there's an entire category of literature, mainly from the work of the great and sadly the late Bruce McEwen from the Rockefeller University and some of his scientific offspring, like the great Robert Sapolsky, showing that chronic stress, chronic elevation of epinephrine actually inhibits learning and memory and also can inhibit immune system function, whereas acute, sharp increases in adrenaline and cortisol actually can enhance learning and indeed can enhance the immune system. So if you really want to leverage this information, you might consider getting your brain and body into a very calm and yet alert state, so a high attentional state that will allow you to focus on what it is that you're trying to learn. We know focus is vital for encoding information and for triggering neuroplasticity, but remaining calm throughout that time and then afterwards spiking adrenaline and allowing adrenaline to have these incredible effects on reducing the number of repetitions required to learn. So if you're like me, you're learning about this information, this beautiful work of McGaugh and Cahill and others, and thinking, wow, I should perhaps consider spiking my adrenaline in one form or another at the tail end or immediately following an attempt to learn something. And yet we are not the first to have this conversation, nor were McGaugh and Cahill or any other researchers that I've discussed today the first to start using this technique. In fact, there is a beautiful review that was published in the journal Neuron, Cell Press Journal, excellent journal, called Mechanisms of Memory Under Stress. And I just want to read to you the first opening paragraph of this review. So here I'm reading, and I quote, "In medieval times, communities threw young children in the river when they wanted them to remember important events. They believed that throwing a child in the water after witnessing historic proceedings would leave a lifelong memory for the events in the child." And believe it or not, this is true. This is a practice that somehow people arrived at I don't know if they were aware of what adrenaline was, probably not, but somehow in medieval times, it was understood that spiking adrenaline or creating a robust emotional experience after an experience that one hoped a child would learn would encourage the child's nervous system, and they didn't even know what a nervous system was, but would encourage the brain and body of that child to remember those particular events. Very counterintuitive, if you ask me. I would have thought that the kid would remember only being thrown into the river. My guess is that they remembered that, but that the idea here anyway is that they also remembered the things that preceded being thrown into the river. So both interesting and amusing and somewhat, I should say, thought stimulating, really, that this is a practice that has been going on for many hundreds of years. And we are not the first to start thinking about using cold water as an adrenaline stimulus, nor are we the first to start thinking about using cold water-induced adrenaline as a way to enhance learning and memory. This has been happening since medieval times. So now I'd like to talk about other tools that you can leverage that have been shown in quality peer-reviewed studies to enhance learning and memory. And perhaps one of the most potent of those tools is exercise. There are numerous studies on this in both animal models and, fortunately now, also in humans, thanks to the beautiful work of people like Wendy Suzuki from New York University. If you recall earlier, I mentioned that learning and memory almost always involves the strengthening of particular synapses and neural circuits in the brain. There is one exception, however, and we now have both animal data and some human data to support the fact that cardiovascular exercise seems to increase what we call dentate gyrus neurogenesis. Neurogenesis is the creation of new neurons. The dentate gyrus is a subregion of the hippocampus that's involved in learning and memory of particular kinds. It's very clear that getting a minimum of 180 to 200 minutes of so-called zone 2 cardiovascular exercise, so this is cardiovascular exercise that can be performed at a pretty steady state. We believe that it is indirectly through enhancements in cardiovascular fitness that there are improvements in hippocampal dentate gyrus neurogenesis. What does that mean? The improvements in cardiovascular function are indirectly impacting the ability of the dentate gyrus to create these new neurons. To my knowledge, there's no direct relationship between exercise and stimulating the production of new neurons in the brain. It seems that it's the improvements in blood flow that also relate to improvements in things like lymphatic flow, the circulation of lymph fluid within the brain, that are enhancing neurogenesis, and that neurogenesis, it appears, is important. Now, in fairness to the landscape of neuroscience and my colleagues at Stanford and elsewhere, there is a lot of debate as to whether or not there is much, if any, neurogenesis in the adult human brain. But regardless, I think the data are quite clear that the 180 to 200 minutes minimum of cardiovascular exercise is going to be important for other health metrics. Now, it is clear that exercise can impact learning and memory through other non-neurogenesis, non-new neuron type mechanisms. And one of the more exciting ones that has been studied over the years is this notion of hormones from bone traveling in the bloodstream to the brain and enhancing the function of the hippocampus. Yes, indeed, your bones make hormones. We call these endocrine effects, so they're effectively acting as hormones. And one such chemical is something called osteocalcin. Now, these findings arrived to us through various labs, but one of the more important labs for sake of this discussion today is the laboratory of Eric Kandel at Columbia Medical School. His laboratory has studied the effects of exercise on hippocampal function and memory, and other laboratories have done that as well. And what they found is that cardiovascular exercise, and perhaps other forms of exercise too, but mainly cardiovascular exercise, creates the release of osteocalcin from the bones that travels to the brain and to subregions of the hippocampus and encourages the electrical activity and the formation and maintenance of connections within the hippocampus and keeps the hippocampus functioning well in order to lay down new memories. So much of our brain real estate is devoted to movement that it's been hypothesized for more than a half century, but especially in recent years as we've learned more about the function of the brain at a really detailed circuit level, that the relationship between the brain and body and the maintenance and perhaps even the improvement of neural circuitry in the brain depends on our body movements and the signal from the body that our brain is still moving. The fact that osteocalcin is released from bone, and in particular can be released in response to load-bearing exercise. So this would be running. Again, weightlifting hasn't been tested directly, but one would imagine anything that involves jumping and landing or weightlifting or body weight movements and things of that sort. That's a signal to release osteocalcin, and we know that signal occurs, that is directly reflective of the fact that the body was moving and moving in particular ways. In fact, you could imagine that big bones, like your femur, are going to release more osteocalcin or be in a position to release more osteocalcin than fine movements like the movements of the digits. And this idea that the body is constantly signaling to the brain about the status of the body and the varying needs of the brain to update its brain circuitry is a really attractive idea that fits entirely with the biology of exercise, osteocalcin, and hippocampal function. Now, I certainly don't want to give the message that just moving, just exercise is sufficient to keep the neural architecture of your brain healthy, young, and able to learn. While that might be true, it's also important to actually engage in attempts to learn new material, either physical material, so new types of movements and skills, and or new types of cognitive information, languages, mathematics, history, current events, all sorts of things that involve your brain. Nonetheless, it's clear that physical movement and cognitive ability and the potential to enhance cognitive ability and the ability to learn new physical skills are intimately connected. And osteocalcin appears to be at least one way in which that brain-body relationship is established and maintained. Next, I'm going to tell you about a study which points out the immense value of visual images for laying down memories. And you can leverage this information, and this involves both the taking of photographs, something that's actually quite easily done these days with your phone, as well as your ability to take mental photographs by literally snapping your eyelids shut. So I just briefly want to describe this paper because it provides a tool that you can leverage in your attempt to learn and remember things better. The title of this paper is Photographic Memory, the Effects of Our Volitional Photo Taking on Memory for Visual and Auditory Aspects of an Experience. It refers to photographic memory not in the context of photographic memory that we normally hear about, where people are truly photographic, look at a page and somehow absorb all that information and commit it to memory, but rather the use of camera photographs or the use of mental camera photographs, literally looking at something and deciding, blink, and snapping a snapshot of whatever it is that you were looking at and remembering the content. 2 years ago, I was in an Uber and I looked out the window and it was a street scene. I was actually in New York at the time, and I decided, for reasons that are still unclear to me, to take a mental snapshot of this city street image, even though nothing interesting in particular was happening. And I do recall that there was a guy wearing a yellow shirt walking, there was some construction, etc. I can still see that image in my mind's eye because I took this mental snapshot. This paper addresses whether or not this mental snapshotting thing is real and raised the hypothesis that if people are allowed to choose what they take photos of, that taking photos, again, this is with a camera, not mental snapshotting, that taking those photos would actually enhance their memory for those objects, those places, those people, and in fact, details of those object, places, and people. And indeed, that's what they found. What does this mean? It means that if you really want to remember something or somebody, take a photo of that thing or person, pay attention while you take the photo, but it doesn't really matter if you look at the photo again. That framing up of the photograph stamps down a visual image in your mind that is more robust at serving a memory than had you just looked at that thing with your own eyes. Very interesting, and it raises all sorts of questions for me about whether or not it's because you're framing up a small aperture, a small portion of the visual scene. That's one logical interpretation, although they didn't test that. The reason I find this so interesting is that a lot of what we try and learn is visual. And for a lot of people, the ability to learn visual information feels challenging, and we'll look at something and we'll try and create some detailed understanding of it. We'll try and understand the relationships between things in that scene. It does appear, based on the study, that the mere decision to take a mental snapshot, like, okay, I'm going to blink my eyelids and I'm going to take a snapshot of whatever it is I see, can actually stamp down a visual memory much in the same way that a camera can stamp down a visual memory, of course, through vastly distinct mechanisms. No discussion of memory would be complete without a discussion of the ever-intriguing phenomenon known as déjà vu. The way this works has been defined largely by the wonderful work of Susumu Tonegawa at Massachusetts Institute of Technology, MIT. I should also mention the beautiful work of Mark Mayford at the Scripps Institute and UC San Diego. Here's what they discovered. They evaluated the patterns of neural firing in the hippocampus as subjects learn new things. Neuron A fires, then neuron B fires, then neuron C fires in a particular sequence. Again, the firing of neurons in a particular sequence, like the playing of keys on a piano in a particular sequence, leads to a particular song on the piano and leads to a particular memory of an experience within the brain. They then used some molecular tools and tricks to label and capture those neurons such that they could go back later and activate those neurons in either the same sequence or in a different sequence to the one that occurred during the formation of the memory. And to make a long story short, and to summarize multiple papers published in incredibly high-tier journals like Nature and Science, which are extremely stringent, found that whether or not those particular neurons were played in the precise sequence that happened when they encoded the memory, or whether or not those neurons were played in a different sequence, or even if those neurons were played, activated, that is, all at once with no temporal sequence, all firing in concert, all at once, evoked the same behavior and, in some sense, the same memory. So at a neural circuit level, this is déjà vu. Whether or not this same sort of phenomenon occurs when you're walking down the street and suddenly you feel as if, wow, I feel like I've been here before. You meet someone and you feel like, gosh, I feel like I know you. I feel like there's some familiarity here that I can't quite put my finger on. We don't know for sure that that's what's happening, but this is the most mechanistic and logical explanation for what has for many decades, if not hundreds of years, has been described as déjà vu. I'd like to cover one additional tool that you can use to improve learning and memory. This is based on a paper from none other than Wendy Suzuki at New York University. The title of this paper will tell you a lot about where we're going. The title is Brief Daily Meditation Enhances Attention, Memory, Mood, and Emotional Regulation in Non-Experienced Meditators. This is a study that involves subjects aged 18 to 45, none of whom were experienced meditators prior to this study. There were two general groups in this study. One group did a 13-minute long meditation, and this meditation was a fairly conventional meditation. They would sit or lie down. They would do somewhat of a body scan, evaluating, for instance, how tense or relaxed they felt throughout their body, and they would focus on their breathing, trying to bring their attention back to their breathing and to the state of their body as the meditation progressed. The other group, which we can call the control group, listened to, of all things, a podcast for an equivalent amount of time, but they were not instructed to do any kind of body scan or pay attention to their breathing. Every subject in the study either meditated daily or listened to a equivalent duration podcast daily for a period of 8 weeks. So the takeaways from the study are severalfold. First of all, that daily meditation of 13 minutes can enhance your ability to pay attention and to learn. It can truly enhance memory. However, you need to do that for at least 8 weeks in order to start to see the effects to occur. And we have to presume that you have to continue those meditation training sessions. In fact, they found that if people only did 4 weeks of meditation, these effects didn't show up. Now, 8 weeks might seem like a long time, but I think that 13 minutes a day is not actually that big of a time commitment. And the results of this study certainly incentivized me to start adopting I'm going for 15 minutes a day now. I've been an on and off meditator for a number of years. I've been pretty good about it lately, but I confess I've been doing far shorter meditations of anywhere from 3 to 5 or maybe 10 minutes. I'm going to ramp that up to 15 minutes a day. And I'm doing that specifically to try and access these improvements in cognitive ability and our abilities to learn. Today, we covered a lot of aspects of memory and how to improve your memory. However, for sake of what was discussed today, please understand that any number of different neurochemicals can evoke or can increase the amount of adrenaline that's circulating in your brain and body. It really doesn't matter how you evoke the adrenaline release because remember, adrenaline is the final common pathway by which particular experiences, particular perceptions are stamped into memory, which answers our very first question raised at the beginning of the episode, which is, why do we remember anything at all? Right? That was the question that we raised. Why is it that from morning till night and throughout your entire life, you have tons of sensory experience, tons of perceptions? Why is it that some are remembered and others are not? And while I would never want to distill an important question such as that down to a one molecule type of answer, I think we can confidently say, based on the vast amount of animal and human research data, that epinephrine, adrenaline, and some of the other chemicals that it acts with in concert is in fact the way that we remember particular events and not all events. Once again, thank you for joining me today to discuss the neurobiology of learning and memory and how to improve your